On with our next talk by Menelaos Sarantos, who's going to be giving the overview talk for parallel session number 4, the interactions between space and planetary surfaces, and he'll be speaking to us about what controls the lunar sodium exosphere. Thank you.
So this presentation touches upon the themes that will be further developed during our session, the follow-up session, namely the effects of dust, solar wind, UV light on the surface, both the surface and the exosphere of the moon. And it will do so by examining the newest observations we've had of the lunar sodium exosphere. We've known sodium and potassium exists in vapor form around the moon since the mid-80s. It's only in the last, and we continue to monitor these exospheres from the ground because of the good scattering efficiencies. But it's only in the last few years that we've had spaceborne measurements, starting with Kaguya in 2009. And these measurements, both ion spectrometer measurements shown in the top, as well as the UV spectrometer measurements, so in the bottom, demonstrated a couple of key things that lead us to reevaluate our theory for how you produce and sustain these exospheres, or at least revise some of the details. For instance, it was found with the ion spectrometer measurements that this atmosphere for sodium and potassium didn't actually, where's the laser pointer? I guess it's not working. If you notice carefully, you'll find that the atmosphere is not centered around the subsolar point in this top panel on the left. It's actually shifted, the peak is shifted 10 degrees towards the dawn. And that over there is clear evidence that the reservoir for the atmosphere is not infinite. Rather, and of course it's not the sodium, the intrinsic sodium in the bulk that gets depleted, it's rather the coatings of sodium from previous ejection events, the recycled particles that get reused, and after the subsolar point, you remove them from the surface with such efficiency that you no longer have the same caverns below. And so that is actually relatively easily explained in a model of the sort that I will describe very shortly. It's just simply the rates of when you put in experiments for photo rates, photo desorption rates, and sputtering rates, and you count flux balance, you find that you can easily reproduce this slight dawn-dust asymmetry with adsorbates. And the main conclusion from this work was that the main point is that sodium and potassium, with this signature, clearly migrate like volatiles, like water. So once you have to count your adsorbates, they start moving towards the poles. So sodium and potassium can be used as trace species for other volatiles. In the bottom, we also see that there was evidence of both month-by-month variation and annual variation, if you wish. In the 7 months that they observed over there, you see a clear variation in the content of the tail as measured over time. It peaked around early February, and it started increasing again later in June. But within each of these months of observations, they also noted the continuous decrease in tail content of the sodium exosphere from first quarter to third quarter as the moon goes through the Earth's magnetosphere. So this is definitely material that we need to explain. LADEE brought even more questions. Recent measurements by the UVS demonstrated the same long-term variation, but now these are measurements on the day side. Shown here, basically the spacecraft's about 50 degrees downwards of the subsolar point in measurements that Tony Koloprick will be expanding on later on. And that's when it points towards the subsolar point at tangent altitudes of about 10 to 30 kilometers. And in this data set, you see even more clearly both the long-term variation, look at how the minima observed near new moon show this trend, first increasing, then decreasing over time. But notice that within every month, for example, you see a clear variation by something like a factor of 2. Also notice how it was observed with LADEE. There were clear correlations, enhancements in the atmosphere at times of major streams like Geminids, and Tony will expand on this in our presentations. When you plot the data in selenographic locations as a function of the selenographic location of the new time, you also clearly see that the atmosphere peaked at lunar phases about 10 to 30 degrees past full moon. So again, this is what we need to examine in terms of our interpretation, what produces this variation and these shifts. And if you look at what I'll be talking about is really what is the monthly variation, which seems to be about a factor of 2, roughly. But if you notice, it actually varies throughout this, 5 months of observation. Sometimes it's something like 60% on some months, and on the very last month, it's more like than a factor of 2. So as it turns out, because of this presence of adsorbates, and it takes a while to get them off the soil, when you inject additional material during showers, it will be a while before you can remove the memory of this shower from the soil. And this is beginning to be shown here in this model, in which, in addition to a steady state model of the atmosphere, and I'll explain how you get this wiggles, which is really the monthly variation that we're going after. But in the red line, imagine that we're shooting an enhanced emission during Geminids, coinciding with Geminids for 5 days. So you will get the red lines here are different lunations, full moons. The Geminids happen about a few days before the moon entered the magnetosphere and reached full moon. You see that you see some initial prompt increase in the atmosphere, you would expect to see at least, but mostly 2 weeks later, you would see that the minima near a new moon are just raised by this additional material you introduced on the night side of the moon, because that's where the radiants are for most of these streams. So this would indicate that this monthly variation, the amplitude thereof, is really affected by all the preponderance of showers that were observed earlier on in the mission. And it's only towards the end of the mission that you really captured the steady state, the atmosphere in steady state. And the point that I'm trying to make today is that this last variation, the last month, it shows an amplitude of about more than a factor of 2. And it turns out it's really hard to explain this with our models. And I will be discussing then what does this variation tell us about both the composition of sodium in the soil as well as the processes that promote it in the air. We previously thought that there is a factor of 2 variation from telescopic observations, and it becomes a bit more obvious when you plot it as a function, plot these observations as a function of lunar phase. We found a few years ago that if you used a model, a transport model, assume a constant content for the sodium exosphere, you could either fit the data at full moon, or quarter moons, when the moon's out in the solar wind, but overestimate the data near full moon, or you could fit the data at full moon and then underestimate the data at quarters. So it looked like you couldn't assume a constant source rate, and the hypothesis at the time was that, once the moon gets exposed to the solar wind or to magnetosheath plasma as soon as it gets near the Earth's bow shock, that promotes, through radiation-enhanced diffusion, the grain promotes more volatiles near the surface of the grain, from which photons can then emit them in the atmosphere. And so we assumed, more or less, that the solar wind affects the yields for photodesorption by a factor of 2. It turns out that these new measurements clearly tell us that this is not what's happening. And so this requires some modification in our theories for how we explain this variation over a month. And three hypotheses that I will be testing today is, one is the source rate for the atmosphere constant, but it's rather the escape rate that varies over a month? Is it that the source rates vary as a function of selenographic location, essentially? Is there more source for the vapor on the near side rather than on the far side? And last, is it a selenographic dependence, rather, of the gas-oil parameters? So this is sort of a flow chart of the processes that generate the atmosphere, as well as a flow chart of the model, from which result I'll be showing. You can assume that impacts refill the reservoir of these adsorbed particles by vaporizing rocks. And obviously, when a meteor shower comes in, you expect those refilling rates to be higher. It is unclear whether UV photons can also excite material directly from minerals and from rocks. But most of this vapor that we introduced either way falls back to the surface, and it looks like from the measurements that we have that it doesn't react, it doesn't become intrinsic again, it remains photosensitive for quite a while. So you keep reusing it, you keep reusing these adsorbed particles until you lose them to the soil wind, either through photoionization or, much more efficiently, it turns out, from soil wind sputtering of these adsorbates. And in red, I identify here all the uncertainty. We have uncertain rates, for example, for the meteor showers, as well as the sporadic, vapor production. We have uncertain yields for photostimulated absorption. We certainly have selenographic dependence of the soil wind parameters because they're modified by magnetic anomalies. So all of this is tracked with a Monte Carlo model in which we trace millions of particle trajectories at any time, counting both the gas parameters, particles in the air, moments like density and velocity, as well as the adsorbed coverage. And this is to show that once you have to go through this long-lived residence time on the soil, the exosphere, the resulting exosphere, has quite a long memory. This is a bunch of particles that I injected in this model from the day side for 1 second, and this tracks how long it would take to remove them as a function of photo desorption and sputtering cross sections. And you can see that unless you lose these particles to the surface, for which no such thing exists in these models, it would take roughly 90 days to eliminate half of them. So the reason is because these adsorbed particles, when you use the experimentally derived cross-sections, remain on the soil for several days before the next photon finds them and re-excites them. And because of the photoionization lifetimes being about 2 days and the ballistic lifetime being only 30 minutes, you actually have to do this about 40 times. 40 times times 2 days on the soil between bounces. That's how you produce a long-lived system. This turns out to be a problem for explaining the monthly variation. So maybe we have a means to explain the long-term trend by the longevity of these adsorbed particles, as well as the peak offset that we see. But now that gives us, as I'll show you, quite a problem trying to explain how do I shake this system by a factor of 2 in a month, if it's so, it has memory of previous lunations. So we know that from this experiment that it's quite efficient to eliminate adsorbates. And so if we assume that the system has constant source rate, but the sputtering rate varies because the moon enters the magnetosphere for some 4 days, it turns out a maximum you will produce about a 30% variation of total content of sodium in a month. This is short of what is observed, which is more than 100%, and it also turns out this yields, this is done as a function of photon-stimulated desorption, PSD, rate, and as a function of sputtering yield. They're somewhat uncertain within factors of 2, but what we conclude from this, it can't just be a variable escape rate. We actively have to do something about the source rates. So the next set of models tests the hypothesis that clearly we need to amplify this curve. Qualitatively, it looks like the data, but something is happening, something strange is happening on the near side. So the next set of models assumes basically a factor of 2 difference between the source rates. This is just a control model in which lunar phase 180, the far side being exposed to photons. We get a factor of 2 less source rate in this model. And this is just a toy model to demonstrate that in this case, if you assume no sinks to the surface, you put in a factor of 2 difference in source rate, but you get only a factor of 36%, 1/3 variation in 1 month. That is because, again, you have injections from previous lunations, and because of particle transport, it's a diffusive process, and you diffuse the difference in source rate that you put in. It gets a little better if you assume high reaction rates on every bounce as a trap function here, but still it's not the factor of 2 that you expect. You can construct more elaborate models here. I assume that the source rate for PSD is proportional to the amount of iron, which varies between the near side and the far side. I will explain why this could be a good assumption. In that case, now you get some about 80% variation in 1 month, and if it actually gets trapped on every bounce very efficiently, maybe you get something close to the measurement. But again, you need to keep those adsorbed particles, right? So a last set of models is actually pretty similar. What if it's not the source rate that varies, but once particles fall onto mare versus highland soils, they have radically different photon-stimulated desorption efficiencies. And here is shown that by assuming 4 and 8 times shorter residence times or photon-stimulated desorption cross-sections, you can begin to produce more of a variation on 1 month. So one word to interpretation now. Basically, what complicates all this is we don't know the inhomogeneity of sodium on the surface. From lunar samples, we know a little bit. Maybe there is a factor of 2 to 3 variation in the soil, but this model just demonstrated that we probably need more than this. So why would photon desorption yields be different on different soils? These experiments demonstrate that if you coat different minerals, sodium on different minerals, you get different threshold for activating this photodesorption or electron-stimulated desorption. When you do this on silicon dioxide, you see you have a threshold of about 5 eV. When you do it on other minerals, it's 20 eV. By then, the fluxes of photons are much reduced. And so this provides a natural framework then for the main conclusion, which is this data indicate that unless there's maybe 10 times less sodium in the highlands than on the day side on mare, we have to assume, we must infer from this data set that the photodesorption rates are a function of selenographic location. They're different on mare than on highlands. And we've seen some experiments with water adsorbing very differently on these soils, and maybe sodium does the same. We have no experiments pointing to that. So that concludes my presentation. Thank you.
I think we have time for one quick question.
That's an interesting hypothesis. One question, though, if it's true.
I'm sorry.
Oh, sorry, Jody Wilson, University of New Hampshire.
Thank you.
If it's true that the sodium is more easily desorbed off of mare than highlands, wouldn't that imply you're going to get preferentially a buildup of sodium in the highlands, and eventually you'll actually achieve an equilibrium because there'll be more sodium atoms to desorb in the highlands. It'll end up being a wash.
Yeah, no, it's not. I skipped this because we didn't have much time, and it doesn't look like I can go easily back. But this is the coverage you would produce in such a model. This is the resulting sodium surface coverage, and you see it's quite in the blues over there. It shows that you emit those particles quicker on Mare, but no, it doesn't help you much.